Cosimo. Good morning, afternoon, evening, wherever you are. Great to be with you again. For those of you that haven't been on a previous one, just want to show you where I'm speaking to you from. It's this southeast corner of the UK, a place called Felixstowe on the sea, nearby the sea. I'm about a mile away from the sea where I live here. It's a very nice place to be. Have to lock down in the countryside here. And this afternoon, evening's webinar is called Don't Forget the Audio. Now, there's a few notices. I know Cosimo said a few of these, but just to point out, the webinars are on the YouTube under nevion.com/YouTube. I'm proposing to do another CTO webinar in roughly 2.5 weeks' time on Wednesday, the 10th of June, on the potential of media production with 5G. There's another seminar coming up on the 26th of May with Nevion and Arista. There'll be more details on that later on as well. And just to say, I know many of you, probably, hopefully all of you, have actually had a chance to meet up with some of our experts, our sales team and our architects over the last 4 weeks in our kind of sort of NAB and post-virtual NAB time. But if you haven't managed to do that, please do get in touch. And if you're having any problems, do just ping me an email. I'm very happy to forward on if you're unable to get hold of who you need to. So this is called Don't Forget the Audio, and the upfront declaration I have to do on this to start with is actually I'm an audio guy. So these are, I just took this before I came on the webinar this morning. This is 2 of the rooms in my house, much to my wife's deep joy. So as you can see, I'm heavily into audio, and I've got a fair bit of stuff that I do with audio outside of my day job as well. So yeah, so I'm passionate about the audio as well, which is an oft overlooked thing in video systems. So just a handful of quick slides, some of which you will have seen before if you've been on previous webinars, just to talk about Nevion and our DNA. So open standards is something we're very passionate about. We invest a fair bit of time in Nevion in helping to actually define and evolve and reiterate standards, and get involved in also, prototyping their implementation. And then, as you'll have seen, and as you will see this morning as well, in promoting it as well. And these 5 bodies here are all bodies that we're significantly involved in as an organization, helping to lead some elements of the work as well. So that's part of Nevion's DNA, and that hopefully means for our customers, there is, an open standard way of doing things. And whilst we believe we're best in breeding technology, there's no lock-in to what we do. Again, most of you will probably be familiar with our portfolio, but just before I get into the technology piece of this webinar, just a reminder, our 2 main solution areas are Video iPath, which is a software management orchestration tool, which is all about fulfilling connectivity and monitoring performance, both within network, on the periphery of network, and doing total resource management. And then Virtuoso, which I call our generic bespoke appliance. We have coming up for 30 software images which we can run on this appliance and under control of Video iPath or another orchestration system. And that allows us to fulfill many of the video and audio and data processing functions that are needed as part of an end-to-end broadcast system. And these triangles I've added on since last week because we've got them. So because everyone was at home and didn't actually do this stuff in March, pre-NAB, we've got self-tested triangles. So we actually all self-tested, every vendor that was taking part in the recent interop tests, self-tested them, provided our results in for verification. So we've got some triangles to add to our nice circular badges that we had from last year. And in the middle there, from baseband to IP to virtualization, that's a booklet that myself and many of my colleagues, including Olivier, our VP of Marketing, have been very involved in writing over the last 5 years. I think we're up to something like version 8 now, and we've been trying to iterate that as we and gradually enhance it as we learn more and as the industry evolves and as standards evolve. So it's a very good reference point, a technology reference point. I would encourage you to get a copy of that, either physically or virtually, if you would like and don't have one already. Just to say, in the last 5 years, we have gone from very embryonic early adopter IP facilities through to it becoming business as usual now, and that's very exciting. We've seen the maturing of the standards of the technology, and I'm going to unpack a few of them relating to audio as we go through today. This is a picture that I've shown at both of the previous webinars, but I'll show it again and just talk to it for a few seconds, because I think it's a very important way of defining what we're doing and the space that I'm talking about here, and how that's evolving really. So the light green facilities, that's all about your traditional campus production campus or facility. We're then looking at OB vans, which have very similar types of technology, generally typically smaller, just less of it, and hopefully more compact. We've then got the classic remote production, which is following different models now, but is tending to be a lighter weight at the event and more at-home gallery type production, and the heavyweight stuff being shared resources back at home. And then distributed production, which to me is the most exciting bit, and that's the phase that we've really hit just in the last 12 to 18 months in the industry. And this is true, of the whole ecosystem, the audio and the video and everything else in the production. And that's where we're actually interconnecting multiple facilities and outside vehicles, etc. Lots of different areas together to share resources. So that's to share processing capability, be that virtual or physical. That's to share real estate, the studio floors, the galleries, etc. And most importantly, to share the people. So all of that's very important. And I think this picture really neatly sums up all of those elements. So we've seen a massive scale up of the number of flows that need to be handled in modern facilities. I think I talked a couple of weeks ago the fact that we've seen like a 10-fold increase over the last 3 years in the number of connections that are needed. We've been touching the 100,000 connection scale in some large deployments. Now, one of the things that's really driving that in terms of scale is audio, and very specifically, since we've gone to our essence-based architecture, which I'm going to unpack in a little bit, that's actually meant that we've actually typically got lots more flows, because the audio is being carried more discreetly in either monos or stereo or 5.1s or 8 channels or whatever. And again, I'll unpack that a little bit later as well. And those things are driving scale, having the different number of signals, along with this distributed and federated production that I was just talking about a little bit earlier on. So winding back to audio, so one thing I just want to do is some kudos. So in terms of facility IP, the audio guys have been doing this a lot longer than the video guys. I've put down a couple of dates there, which I think are accurate. I think Dante, over IP, this is specifically over IP rather than Ethernet. So Dante over IP in 2006 and Ravenna in 2010, which obviously are both well ahead of the 2110 suite. And as you'll see, the 2110 suite in the audio space has leveraged the if you like, the inheritance of what some of these previous more proprietary formats have actually given us. So this is a little diagram I put together to try and just show some of the things I want to talk about for the next few minutes, to give you an idea of some of the elements. So key to this is obviously we've got our production center. You'll see I've got my ubiquitous little satellite logo top right. So we're actually time referencing that, and we'll unpack a little bit more about timing referencing as we go through this presentation. But all of the elements within that production center, be they video or audio, are obviously running and referenced to that timing reference. Very importantly, we've got alternative locations, and I do want to unpack some of the challenges and some of the thinking about alternative locations. I also just want to say, as a big thing at the top end, and I'm going to come and mention it towards the end of the presentation as well, that it's very important that security is actually tackled. And I think possibly some of the way that the early IP facility audio systems have been developed, probably security wasn't first and foremost in mind there. And I think, as an industry in the last few years, there's been a vast amount more focus on security. And again, we'll just unpack that a little bit as we go through the session. Okay, right, just trying to move things so I've actually got better sight of what I've got on this on the screen here. Okay, so I want to just jump back in time just to pay kudos to some people that did some crazy innovation in audio, or specifically in sampling, really, back in the day. I was actually amazed to see some of this pioneering work. So on the right-hand side there, you'll see the first disclosure of a PCM system, pulse code modulation, was back in 1921. And even ahead of that, there was a guy called Rayner in 1903 who actually did some work on the rate that you need to sample audio at to actually get intelligible speech. So that was done back with mechanical sampling in 1903. And then the work that everyone's aware of by Nyquist was in 1924. And then jumping forward in time, we have a couple, I think these are both classics. This is unbelievable. So we've got a 50 kilocycles per second analog to digital converter on the left there from 1954. It took 500 watts of power and weighed 150 pounds. So just a crazy piece of equipment. And then Analog Devices, one of the first hybrid analog to digital converters, a 12-bit converter back in 1977. I can recall when I was doing a university project developing a digital audio system in 1986 or 7, getting them to buy me a 14-bit A to D converter. And I think at that time, I think it cost about £250. And I think the head of department was very, very anxious about me doing that. Anyway, so it's amazing how this technology has evolved, especially with respect to audio and what we can now do. Just think of the quality of the sample rate conversion that you've actually got on your phone and in so many other devices, even in your headset. So audio acquisition. So just a few more fundamentals before we jump into the specifics of the application of the technology to facilities. So this is obviously a very fundamental thing. There are two key things as we do this PCM sampling of the analog signal. One is the frequency at which we sample it, just referencing back to that work from 1903. And then the bit depth, so what resolution we actually have of that sampling. And then importantly, and I'm going to come on to this in a little bit, is the time of capture. And that's definitely a very important element as we actually create our systems and build them together now. Now, there's lots and lots of different audio interfaces and formats in existence. So, these categories probably aren't quite, fair. But so on the left-hand side, I've kind of outlined, standard ways of doing audio, and then on the right-hand side, some of the very popular proprietary formats. And when I say proprietary, I'll unpack a little bit what I mean about that later on. But a lot of these are very well proven and excellent technologies that are working within campus production environments. And the EBU did some work probably must be about 12 to 14 years ago with 3326, and then obviously AA67 came along, and then relatively recently the 2110 suite, which leverages effectively the inheritance of both of those. So one overall comment I think on this audio production interconnect is that, looking back at all of those things I just had on the previous slide, the proprietary ones as well as the standard ones, the actual data flows have almost an identical approach. It's carrying the audio PCM data packed into RTP UDP packets, and I'm going to talk about that in a minute. But the control plane is where it's very different, and we'll do some unpacking of that again, and that's where some of the challenges lie as we actually move to a fully interoperable future. So I hate slides with lots of text on, as hopefully you'll have seen, but I thought I'd put this one up just because it does show some of the challenges of where we've come from, and just the sheer number of choices that we've got within the audio. So the top two are obviously not IP, they're pre-IP. There's AES3, which is our beloved digital audio interface, stereo interface, which we've used for many years, and with a variety of sample rates, although obviously most people have probably been using either 44.1 or now 48 kilohertz for broadcast. And we've got the different bit depths and effectively the frame period. It's a constant number of samples, so the period of AES frame is determined effectively by the sample rate. And then we had, or around the same time, still both a long time ago now, we've got the MADI, which basically allows us to carry up to 64 channels. Up to 96 kilohertz and up to 24-bit resolution. And interestingly, it's been interesting to observe that the resurgence of MADI in recent times, possibly because it actually has become a useful, if you like, neutral handover gateway point between some of these other proprietary audio formats. And then in more recent times, as we come to the IP domain, and we've got AES67, which theoretically can actually handle up to 120 channels of audio within a flow, although the mandate is being up to 8. A variety of sample rates, again 48 kilohertz being the standard, and the packet variety of packet periods, again 1 millisecond being the typical one. And then 2110-30, which is part of the suite that we've been talking about in some of these webinars. There are 3 levels. There's level A, B, and C, and effectively what 2110-30 is, it's a subset of AES67. So we've chosen the mandate is to be able to support 1 to 8 channels at 48 kilohertz with a 1 millisecond packet period. There are then extensions if you want to go up to double sample rate to 96 kilohertz, or if you want to go up to 64 channels, or if you want to go down to the 125 microsecond packet period, which is in fact essential if you want to go up to 64 channels, because you can't fit 64 channels in the packet unless you go down to 125 microseconds. So that's just kind of a bit of a revision and the history of some of the ways we've been carrying digital audio. How that fits into the SMPTE suite, I'm not going to talk to you about all of these. I unpacked them a little bit more, a little bit previously. So just to draw your attention, the relevant ones for the audio, there is the system blob there in part of the SMPTE 2110, the -10. That defines, in fact, the overall way that things hang together in terms of timing. Then there is the -30, which effectively is the PCM audio. That's the pure derivation of AES67. There is then the -31, which I'll just talk to a little bit briefly later on, which is very specifically transparent carriage of all 32 bits of the AES3, andVe got a diagram about that later. Just the other couple of things to draw your attention to, which are up and coming, which are relevant on the sort of data plane, is the fast metadata and FMX-41 and 42. These are ways of carrying small packets of information, descriptors about the actual RTP flows that can be sent in parallel to give you fast updates of information pertaining to the streams. And we'll talk about that briefly. And then that bottom layer is all about the control plane. And again, we'll unpack that in a little bit more detail as we go through. Many of you will know I have a passion of lots of things to do with time. So I just want to unpack, throughout the webinar, I'm going to be unpacking a few more bits about time as we go through here. Several people in the world have had quite a few views on time or comments on time, as you can see here. So it's not just me that's fixated with it. So there's a lot of stuff that we need to use timing for. There is the PTP timing, which is what we're using as the underpin for all of the timing referencing for 2110, was already in use by the audio guys. So AS67 was already using 1588. There's a few nuances as to the profiles and the way it was being used, which are being unified now. They're less of a problem than they were a couple of years ago, so I won't go into that. But 2059 is a very, very important specification because that defines how we actually get the referencing of both the video and the audio from within the system that we use. And then how we actually get time. Obviously, there's lots of satellite-based systems we can use, and there's on-the-wire systems with timing as a service where we can acquire as well. And obviously, the timing and the referencing is very important, right down to the precision of the timing that we actually do the sampling with. And those of you that have done audio theory will know, just getting back to the theory again of it, that that point of the accuracy of the clocking in which we actually sample that original audio as it's coming in is very important. Also, just worth saying, obviously, more and more devices now are inherently presenting the pre-acquired or pre-digitized audio flows. So another slide you'll have seen before is my RTP slide. And again, just to reiterate, RTP is absolute king for real-time flows. I think that's been everything that's been built in AS67 and simply 2110 is based upon UDP RTP. And the key thing about RTP is it gives us two things. It gives us sequence numbers of the packets, so we know if they've gone missing, and it gives us timestamps. So those timestamps do help us with two things. First of all, knowing about the source timing, and secondly, allowing us to determine if there's been issues in the transport of the timing. So moving to that source timing, or as I'm calling it in this slide, origination timing, one of the key things about the acquisition of both the video and the audio in the 2110 system, and obviously inherently in the AS67 as well, is the fact that the RTP timestamp is used to take absolute time away, a 32-bit subset of absolute time, if you like, and actually create a timestamp at the point of acquisition of those video images and of the audio samples. And what happens with the audio sampling in RTP is the actual timestamp ticks at the sample rate. So effectively, every time we take an audio sample, we actually have we increment the timestamp number in the RTP flow for the audio. Just an observation, because we're going to come back to a couple of nuances of RTP in a minute. In video, we've actually, should we say, manipulated or deviated, that's probably a better word, from the original RTP definition, in that the timestamp is actually frozen for all of the packets relating to a video frame in the video flow. So you actually get this step change of timestamps in the video flow. So it was done like that so that all of the information regarding one video frame actually has the same timestamp. Probably not, well, definitely not how RTP was originally intended to be used. So control plane. We've talked about the data plane. We've talked about how even the proprietary standards, the data plane is largely pretty well identical, but it's the control that's very different. And the control plane of 2110 is something that came later. It's not part of 2110. It's actually AMWA NMOS specifications. We've got this toolkit specifications. Those four at the bottom are relevant to audio. Some of them are relevant to the video as well. But so ISO 4 is how a device registers itself and says, hey, I'm an A to D converter. I've got a micro, representing this microphone. This is what I'm doing. This is what I can give you. ISO 5 is about connecting to sources. So that's actually how you actually create connection of devices to source flows. ISO 7 is all about the timing of events. So if I push a button on an intercom system, if I move up a fader on a control surface, if I switch a tally light on a camera, all of those elements are functions of things that are happening at a defined time, and we need to send messages to represent that fader value, that button push, that tally light, and that's being defined in ISO 7. It's called event and tally. And an ISO 8 is, if you like, is an addition to ISO 5 in a kind of way. It's been defined to actually help manipulate streams that contain more than one audio channel, because if you're sending a single IP flow that's got multiple audio channels in it, then ISO 5 only addresses the IP flow, so it doesn't actually do anything about the content. Whereas ISO 8 allows you to effectively do shuffling or manipulation to define what audio needs to be used by a device. So, for instance, if, as a trivial example, if I've got a set of surround sound speakers that are wired digitally using that, then I need to tell each speaker which of the 6 flows that's contained within there it needs to take, just as an example. So this is really maturing, but obviously we're still in the audio world, got a lot of systems that are effectively have proprietary control plane as well, but more on that in a little bit. Another thing which has been done as part of the 2110 suite is the SDP. So this is, if you like, just a statement of capability by a source to actually say what it's got, what it's capable of, and that information is made available and is then usable. It goes into the registry, so other parts of the system can actually see this information, see the SDP of the sender. So because the actual flow itself is basically, in the audio world, is pretty well audio PCM samples just packed with the RTP header and the other IP headers on it. That doesn't have any metadata that describes it. Now, obviously, with some clever measurement, you can actually determine a fair number of things about an audio flow just by post analysis. But this has been the way we've defined that we actually declare everything that's important about a source. It's worth saying that obviously an SDP is a relatively slow moving, slow updating piece of information. So obviously most streams are going to be pretty static. You're going to put them up and they're going to be there either in perpetuity or at least for several hours. Because some streams in production environments are dynamic and change, and you actually need to harness those changes quickly, there's a couple of additional standards in the 2110 suite, this -41 and 42, which are still being worked on, and my best guess is that they're going to be available by the end of the year. And those are for sending fast updates effectively of the information that's in the SDP, this source descriptor information, sending fast updates of those. Now, in the IP domain, just like in the baseband audio domain, we actually need to do some classic things to audio flows in transit through a facility. So, we have always needed to do gain adjustments on audio as it's been in transit. We've needed to do delay compensation, and I'll come back onto some automatic delay compensation topic a little bit later on. Shuffling, so obviously, again, coming back to what I was saying about multi-channel audio, if we've got a flow that's got multi-channel audio, then we may need to extract one stereo pair from a group of 8 channels that maybe has 4 different stereo pairs in it. And lastly there, we may want to downmix, and I'm not talking about kind of intelligent dynamic downmixing of multi-channel stuff. I'm talking about, folding down stereo to mono, some of those basic tricks that need to be done as part of a workflow. So those are all toolkits within the IP domain. Specifically on shuffling, just to actually think about, this manipulation of audio. You saw on those earlier slides, we've got a massive number of variants. If we look at the number of channels per AES flow, if we look at the sample, the packet period, as well as you know, the sample depth and rate, etc., then there's a whole load of different variables there. And different people have been proposing different ways of actually how we actually manipulate the audios. Some people have been proposing that actually the best way to have the simplest way of manipulating the audio from everywhere to everywhere is to actually send every individual audio channel as mono. Obviously, because of the timing information associated with it and the timestamp, we can actually reconcile, you know, coherent stereo pairs, you know, sample accurately because of the timestamp information. So that's a viable thing to do from a technical perspective. However, the sheer number of feeds we get then is crazy. You know, if we think about a traditional SDI feed that's got up to 16 embedded audio channels, if we're actually pulling that down and we've actually then got, you know, 16 separate audio flows, that's actually potentially quite unmanageable. More on that shortly. We've then got the AES67 here, but when I've put AES67 on this diagram, I'm using that a la simply 2110-30. So I'm kind of using those phrases interchangeably. So I'm referring to the subset of AES67, which is 2110. The middle ground there, which is with the red bits, if you like, that is the concept which we've been doing as solutions in the last couple of years, mostly, where actually different pieces of studio equipment have got the ability to take certain packet period timing audio flows, and they need certain channel widths. So it's impossible to do it without having some form of manipulation. So one of the things that we've been focusing on within the toolkit of software building blocks on Virtuoso is audio processing, both video and non-video related audio processing. And I've got a couple of diagrams on those in a minute. But that allows us to actually, if you like, have that IP audio processing almost as a service which you can route to within a facility. So you can bring in maybe a 64 channel wide AES67. You can break out some monos for commentary, which you can send one place. You can break out some stereos. You can break out 5.1s, whatever you need to do. You can obviously within that also do the delay. You can do the gain adjustments you want to, etc. So a lot of flexibility there. Obviously, the bottom option is basically obviously you send everything to the end device and it selects. But I say, as we've seen from actually integrating real solutions in the last couple of years, lots of end devices are very fussy or very particular in terms of channel width, packet periods and sample rates, etc., that they can support. So we need intelligence to actually do this processing, and that's something where we've actually seen a great deal of need for the kind of capability that we've actually developed on Virtuoso.
Andy, quick question.
Yes, go, Cosimo.
Michel Ladmar has a question. Why do you use a separate SDP file? Could this information not be embedded into the signal data flow?
So I missed the first part of that question. Can you repeat it again? Sorry.
Why do you use a separate SDP files? Could this information not be embedded in the signal data flow?
Yeah. So absolutely, it could have been. There were some decisions made, if you like, at the very head of the work on 2110, and I guess because we were one of the methodologies that we had in developing the 2110 standards was to effectively take, where possible, take existing standards or mappings that have been defined. So there were already mappings for PCM in audio into RTP a la AES67. Similarly, there was also RFCs for mapping video samples into RTP, and none of those actually contained header extensions which gave the information, allowed the information to be natively in the stream. So on one level, it's quite tidy to actually have separate descriptors. On another level, it's quite a pain. And I guess if you look back even as far as AES3, which we all have come to know and love, that AES3, there's a data channel, that 1 bit per AES, 32 bits of AES, which actually is the descriptor channel. It defines everything about it, the sample rate, the professional mode, lots of different things are actually contained within that descriptor. So that inherently has in-band information. So in some ways, this is a retrograde step, and I think we can look at it in different ways, but where we're at with the standard is we have the SDP, which is effectively our virtual document that describes our sources, and then we've got the FMX, this fast data packets, which we can send to update when things are changed. And as I did allude to, quite a lot of basic behavior can be actually determined from the stream itself as you move down. But obviously, that's the basic behavior about the actual the sampling structure of the signal, not whether it's actually what language it's containing, and then the other metadata that may be absolutely pivotal to what you're going to use. That kind of stuff is in the SDP or in the FMX as we move down this year. So yeah, possibly not an ideal outcome, and with hindsight, maybe we should have done things differently. But it was definitely a compromise between inheriting existing technology and moving it on versus actually writing something from scratch. And I think overall, we made as an industry the right balance there. Audio templates. So the talking to a couple of our solution architects that are doing this, day in, day out, looking at the way things need to be designed for actual facilities. Going back to that concept we have of, do we actually do everything mono, or do we have pick and mix of like every format possible? Actually, in the real world, the way we're doing designs is we're typically having some templates where we would have a small number of audio options. So I've just outlined here an example of kind of 4 audio options. There may need to be a couple of others if we've got different packet period requirements, but typically, assuming this is kind of a classic 1 millisecond packet period work, then 1 channel audio obviously required for intercom and individual commentary feeds, that kind of stuff. Stereo 5.1 carrying 6 channels, and then typically we see people carrying bouquets of 8 and sometimes 16 as well, just to carry. That's almost for legacy transport from what was embedded in SDI. But also, if we're in some countries that have got multilingual production, then 8 channel bouquets is 8 channels within a stream is quite good, because you can actually carry 4 stereo programs, and then you can select which language you want downstream. So although there are those myriad of options, if we boil it down, then actually a few templates for standard ways of doing it is a good approach. I mentioned, I'm just going to talk briefly about the approach that we've had to kind of engineering this in Nevion. So we've got what I call video associated audio format interfacing. So this is everything to do with audio as it hangs with video. So that can be hanging with video as native SDI. That can be hanging with video as a 2022-6, which effectively is the whole SDI. This is the whole SDI stream that's been digitized. So to extract the audio, you've got to do effectively an SDI de-embed once you've depacketized the IP, if you like, the SDI from the IP. And then you've got your native 2110-30, which is obviously video related, but a separate essence flows. So we've got one building block which we developed, which was all of that video associated audio. And then we've been doing some work on audio only, where typically we bring in bouquets. And I've said Maddie's had a resurgence. We've actually done more with Maddie in the last 3 years than we did in the previous 10, I think. So those 64 channel Maddie bouquets coming in, which typically we may want to reconcile timing. So I say over there on the right hand side, I talk about asynchronous, but typically we need to sample rate convert those into the domain. Obviously, that's assuming they're just PCM and they're not other digital audio formats, and I'll come to that later. And then obviously we're reconciling classic AS67 and other -30 and 31 streams, as well as bringing in native AS3 and analog flows. Now, typically, most of what I call the existing pre-AS67 or audio systems in the world were designed for campuses. They were designed for local area. They're designed for a layer 2 environment from the IP perspective. And that's where they really flourish. What we're seeing, if you remember back to that diagram of earlier in the presentation I showed you at the top, where we're moving to this distributed production, where we're going possibly internationally or certainly between multiple centers nationally, we've got wide area connectivity involved. That means there's quite a lot longer latencies involved in round trip, and a lot of those kind of traditional audio systems weren't designed to handle those kind of long latencies. We've potentially got non-synchronous audio as well, because although every campus is typically in the PTP locks, you've got large phase offsets, and you can't guarantee if someone's doing a remote commentary feed from a home office to come in. You've got lots of time reconciliation of asynchronous stuff. And specifically, when we go to these larger networks, we need rooted networks, because layer 2 networking doesn't scale for what we need. So things have to be capable of running in a layer 3 environment, and there's a lot of restrictions there. So these are some of the challenges that we see with what I call, they're not legacy, existing audio infrastructure as we move forward. So there has been various approaches. We've ended up in various solutions interconnecting what I call audio islands, either within campuses or between campuses, with kind of virtual tie lines which we manage. So if you like, gatewaying into more standard interface. And again, the key challenge here is typically the control plane, because there's a lot of messages involved in the existing IP, audio IP systems, that actually is the way that their plug and play toolkit works within those islands, which, yes, doesn't scale and doesn't necessarily work when you're going long distance. So as we morph into hopefully a more standardized world, making use of the full 2110 capability, then we need to look at how we actually can reconcile some of these plug and play toolkits in these proprietary islands into those systems. And we've been using a lot of work with our SDN orchestration to provide deterministic connectivity there. Back to time for a couple of minutes here. So one thing that AS67 did think about very carefully was actually defining presentation time, defining an offset. So when you actually send a signal, you define when that's supposed to be presented. This is kind of a diagram taken from the AS67 specification, and what you can see here is we've got the IP network transit, and then we've actually got the audio manipulation each end, and we've got this timing reference of this link offset between the ingress and the egress that we're handling there, and defining how things are presented. Now that's well and great on a per link basis, and that does mean that the time, you're actually creating time-bound and deterministic presentation of the audio flows when you actually reconstruct them. However, it doesn't play into some of the potential that we have within the 2110 ecosystem of actually honoring the original source time as we propagate through a system. And let me explain that a little bit more. I've unpacked this in previous seminars with respect to video, but just a little bit on audio. So currently, in an AS67 world, the only way that we can actually define use time is effectively creating those, is having an orchestration system that accumulates the link offset time, and actually sums all of those as the signal, as the audio flows propagate the production chain, to actually work out what the total latency is incurred. And then if we've got other media flows that are transversing by other routes, be it different audio flows or typically in a production environment video flows, then we have to accumulate those in a different way to actually work out the reconciliation of timing at the use time on the right. One of the kind of holy grails that I think I originally hoped for in 2110, and it's taken up to the revision that we've just done on the -10 for 2110 to actually get here, is actually having being able to actually honor origination time through the processes, both in the audio domain and the video domain, such that at any point in the system, you can automatically reconcile your essences because you know the origination time of them as they go through the system. So some manufacturers, including us, have done quite a lot of work already in carrying this origination time through various processing elements. But for everything to work in a truly time reconcilable world like this diagram shows, everyone needs to do that. And at the moment, none of the existing AES-67 systems out there actually do that. I won't dwell on this, just to say, obviously, as we reconcile video, if we've got video and audio coming in together, as we reconcile video, then we need to actually, we need to mirror that buffering approach to the audio flow as well. And obviously, to be compliant with things like Dolby E, etc., we need to do integer frame boundary manipulation of the audio flows to make sure that we're tracking the video and we're actually not screwing up any potential compressed audio flows. I think a lot of systems, as they were originally designed, had sort of native media processing, and they've had IP interfaces on the front and back end, which is why timing reconciliation and propagation of origination time was not possible. I think the architecture, the kind of thing that we're using in our designs now, is more like this, where we actually see what time those packets arrive in. We understand what our propagation time through our processing is, and we can reconcile the same audio samples and the same video frames to the same timestamps as the egress. So that's an important kind of architectural element. We've talked about PTP as being the timing reference for everything out throughout the chain. One thing I've observed in the audio domain, specifically in the audio domain, I think, is a lot of audio equipment typically has had what I call a very non-graceful failure scenario if it loses its timing reference. Now, most pieces of equipment from most vendors are going to be pretty pristine in terms of the timing reference they have and their ability to, if you like, freewheel, to hold over time. So one of the design criteria that I know that we've been looking at internally, and I know other people are trying to look at as well now, is to make sure that we have decent holdover times. We should be able to sustain a flow if we have a glitch in PTP of not only 1 second or a fraction of a second, but we should be able to sustain a glitch in PTP of 10 minutes and still actually maintain a decent tracking audio. And the same applies to the video as well. But I've seen many systems, early systems, digital audio systems, where as soon as the PTP reference is lost, it goes to mute. And whilst that's an understandable behavior, it's a bit of a strop, isn't it, to say, okay, I've lost my timing, I'm just going to throw everything up. So I think the industry is on a mission to get better at making sure that actually we gracefully handle issues with timing references. I talked about the requirements of -31, and I'll just bring you this diagram just to talk about the fact that in -31 we are actually carrying that whole shebang, all 32 bits. So if you like, the 24 arguably plus 4 bits of audio, so up to 28 bits of audio, plus those other user data flows. And the reason for that is some compressed stuff. I mean, Dolby E is probably not a good example because Dolby E can sit within the 24 bits of audio, of PCM audio, but some other systems make use of some of these other data bits. So for the non-PCM transport, -31 was defined, and the concept of -31 is you just carry the whole shebang, the whole AES3 is carried. Then everything is fully transparent and there's no ambiguity. As we go off campus, when we're in a federated distributed production environment, there are lots of things. Again, I've used this diagram before. I'm not going to talk you through it in detail today, but there's the concept of different timing domains, different IP addressing schemes, and what I've used the term exotic protocols, which I stole from my friend Martin. That's talking about some of the proprietary stuff, because if we're having to island some audio, especially some of the proprietary control elements, then we need to rein them in and keep them within our campus or within our islands within the campuses. There's a lot of work going on with this on this 2110 over WAN activity group that I'm chairing at the moment. It's been dealing with how we transport the media and what's proving to be the even more complex bit, how we actually deal with the control plane. If you'd like more details about that, do get in touch. I'd love to share with you, but that's ongoing work, which is getting hopefully fairly close to fruition now. As we go on and off campus, we may want to consider other things as well that we definitely don't use in campus. So 2022-7, which actually is being used a lot for video in campus, less for audio at the moment, and FEC, which typically is not used in campus at all. These protection techniques are in use a lot. This is an example of a recent deployment that we've done, an international deployment where we're doing lots of transit of video and audio. Typically, we're actually compressing the video when it's going internationally to a mezzanine compression rate, and then we're discreetly and separately handling those audio flows with those dual diverse routes to be handled and go across the connectivity both nationally and internationally. So there's some significant scale of usage of these things now working in large scale long haul networks. Just while we're on audio, just because it's part of the audio ecosystem, Intercom interoperability is another interesting thing. Again, some vendors are now using standard AS67 audio for the audio bit, but again, all the control piece is proprietary. Back to security, I said we'd start and end with security. The beauty of a lot of the existing AS67 or the proprietary systems that are AS67 like, that are very well formed and very plug and play and functional is because they're plug and play, a lot of the way things happen is not necessarily as secure as it needs to be. One of the things that we've been learning as we've done network design is that for full security, we need to manage connectivity. So have everything being able to be automatically join anything without any verification is a relatively dangerous approach to actually how you actually secure connectivity. So the SDN approach that we have with the video iPath is capable of doing within the Nevion architecture is very important because it allows us to actually control each individual flow, both for the audio and the video and the other data, and very, very specifically the PTP timing and the control data as well. So security first and last. I won't dwell on this, just want to draw your attention to the fact that I did in the previous webinar talk a little bit about the future and how I think that might go in terms of time aware but non-linear time processing. Again, I won't unpack that here, just want to give you a little plug to reference back to that. So hopefully that's useful. So hopefully I've given you a little bit of an overview, a little bit of a history lesson, but also some thoughts on some of the challenges as well as some of the kind of ways to architect things as we go through. We have a team of unbelievably knowledgeable experts in our architects team who have been doing some pristine designs for audio in facilities over the last few years. And these guys would love to share their knowledge with you. So we've got various ways of that happening, but please do speak to your account team or director or architects if you've got their contact details. We'd love to help you through your designs and help you make the most secure, safe, and flexible and extensible networks so you can really leverage the benefits of IP, both with audio and with video. And as I always say, if you're ever in the UK, if we're ever allowed to travel again, then I'd love to make you a nice cup of tea. Mine ran out a long time ago. Actually, the last bit got cold. We have about 3 minutes. Cosimo, do we have any other questions?
Well, so far the only question was with Michelle, and okay. So far I don't see any other. But let's give a few more seconds to figure it out if anyone has a questions. I think it was very clear from the very beginning.
Okay, well, my phone number and my email are on this slide here. So if you want to reach out to me directly, would love to chat. Or if you'd like to challenge me on anything I've said as well, please do that as well. Thank you for your time, everybody. That's been great to be with you again. And we'll be sending out, Cosimo will be sending out details of my next webinar in about 3 weeks' time, and the other ones that are going to be coming up as well on other topics from other people. So thank you very much.